So this work was developed in collaboration with Yihui Chen, and Ruimin Sun, Engin Kirda, and Long Lu at Northeastern University. So the outline of this presentation, I'm going to start with some introduction to embedded systems, the security issues related to these devices, the motivation and threat model of this project, then DBox design, implementation, evaluation, and some conclusions. So embedded devices are ubiquitous and adopted in critical areas, for example, intelligent factories, healthcare, smart homes, and the automotive industry. Because of the importance of these devices, they are the target of major attacks affecting essential infrastructure. Also, in the last few years, security researchers have identified critical vulnerabilities that expose millions of devices to high risk. To defend against these attacks and mitigate vulnerabilities, the security community has developed methods based on static analysis or dynamic analysis, attestation, and compartmentalization, which is the main topic of this project. So essentially, compartmentalization provides two properties. The first one assures the principle of least privilege, and second, restricts attacks or crashes within specific boundaries. Besides the benefits of compartmentalization, the state of the art in this area is limited. It is imprecise because of static analysis limitations, or it is impractical because it requires complex security policy definitions. It is incompatible with real application because it requires hardware modifications that are not available commercially. And also, something that is more concerning is that these solutions ignore or barely support DMA operations. So the question is why supporting DMA is so fundamental for these devices. So takes this smartwatch as an example. So this device has two types of communication channels. The first one uses slow communication through MMIO operations. And this type of the data flows usually are protected by the memory protection unit. But the second type of data flow use DMA-enabled communication channels, which, for example, are used to write data streams with high throughput and high performance. Also, DMA-enabled channels are used to read data from peripherals, while the core processor is in the power-saving mode. And this is quite important in this type of devices because these devices usually are powered by batteries, so saving power is very important. Besides power and performance implications, DMA can affect the security of the system. For example, confuse the deputy vulnerability in the firmware can be exploited to force the DMA controller to read and exfiltrate data from memory areas that were not meant to work with DMA. And in general, if the DMA controller is compromised, it can read or corrupt any memory area because the MPU does not interpose any of these operations. So to solve the current limitations, we introduced DBox, DMA-enabled compartmentalization for embedded applications. And DBox defines a reference architecture and a systematic approach to enable operations. Our approach includes procedures for MPU region configuration, DMA controller reconnaissance, kernel hardening, DMA policy definition, and a signal and exception handling method. So DBox architecture is based on FreeRTOS-MPU and their Cortex-M profile. We selected FreeRTOS-MPU because it is the most popular RTOS for deeply embedded devices, and the Cortex-M is the most popular embedded architecture so far. However, our design is compatible with other embedded architectures and RTOS. DBox defines tasks as the unit of compartmentalization, which are configured during the development phase, where developers define the memory areas, peripherals, and access methods that are required to implement a specific functionality in the embedded application. DBox also uses a capability-based security policy to validate DMA operations, And these operations are served by a trusted DMA task, which is the only one that has access to the DMA controller. So this is an example of the capability-based security policy enforcement. So in this case, task number 1 is the owner of 3 capabilities to access user, SPI, and ADC peripherals. And let's say that the task 1 sends a request to access the user peripheral through DMA. Because the task 1 is the owner of a capability that grants read permissions on user, then the security policy is validated, and the DMA task configures the DMA controller, and this operation allows the task number 1 to read from the user peripheral, right? On the other hand, if task number 1 requires to write on the user peripheral through DMA, then the security policy validation will fail, and in this case, Dbox is going to handle this exception with the procedures that we also define here. We use the capability-based model because it mitigates confused deputy vulnerabilities by design, which in comparison with other models like access control lists, the mitigation of this type of vulnerabilities requires complex validations that are error-prone and not suitable for embedded devices. So we developed a prototype of Dbox for the Cortex-M architecture for the FreeRTOS-MPU version 10.4.1. And the total implementation is around 1,400 lines of code, including the DMA task and the kernel extensions. We also use simple C code structures to define the security policy, like the example that is shown here, which echoes our design goal of applicability on real applications. So as you can see there, we have simple references to peripherals, then access permissions, and the last one that is an extended permission for off-chip peripherals that is a quite unique characteristic of this project. For evaluation, we evaluated Dbox from 3 perspectives: security, performance and power requirements, applicability on real-world scenarios. So our setup includes the development board Nucleo L152RE provided by ST Microelectronics. And this board has a Cortex-M3 running at 32 megahertz. It has 512 kilobytes of flash, 80 kilobytes of RAM, and 2 DMA controllers. The baseline that we compare to is the vanilla FreeRTOS 10.4.1. and the hardware abstraction library for peripherals that is provided also by ST Microelectronics. The tooling that we include to collect performance metrics is the Perception Tracealizer, and for the power monitor INA 2026 provided by Texas Instruments. For the qualitative analysis, we use memory region ratio metric, which measures the effectiveness of a compartmentalization solution. And specifically, this metric calculates the ratio of the memory areas that are exposed at a given time when a task is executed to the total size of the memory area. So we achieve here, Dbox reduces the region ratio to 0% and 1% for peripherals and user space flash. And also, Dbox maintains 0% of the region ratio exposed in the kernel space. So we achieved this result thanks to the stricter configuration of the memory protection unit and the isolation of each task code. Particularly, the kernel memory areas uses also a higher number in the MPU regions, which cannot be override by user-defined regions, which is actually one of the main weaknesses in the original FreeRTOS-MPU. Second part, we also evaluated the number of return-oriented programming gadgets that includes our implementation, and Dbox only adds 10 new gadgets. It also exposed 13 gadgets from the user space, which only represents 2.4% of the total number of available gadgets in the user space. This result is also related to the stricter D-box MPU configuration. We also perform a qualitative analysis comparing D-box with the state-of-the-art solutions. The result here shows that D-box has complete and intrinsic support for DMA operations. And the only solutions that partially support DMA are Microvisor and TOGOS, but in this case, Microvisor is already deprecated, and TOGOS does not consider the diversity of the DMA controllers, which in turn can overexpose sensible memory areas of the DMA, or memory areas that the DMA controller can have access. It is important to notice that D-box is the only one that supports extensible access rights, which are meant to handle off-chip peripherals connected to SPI or I2C buses. Without considering this addressing scheme, DMA cannot operate on this communication bus peripheral. So if there are any solution that does not consider the addressing scheme of these peripherals, then those solutions are actually not compatible with real applications. In terms of performance, we analyze the impact of D-box on the kernel. So we conducted a micro benchmark, and we have a very low overhead, around 1.74% for the context switch routine. We also perform macro benchmarks, where we perform read and write operations for peripherals. And here we have an overhead which is inversely proportional to the size of the data that is transmitted. For example, here, when we transmit one single byte, we observe that we have a relatively high overhead of 134%. But for the same operation, when we transmit 50 bytes, this is around 10%. And for 100 bytes, this is almost zero. So this is actually an expected result because DMA is using high throughput communication channels. So in real applications, the impact is almost negligible. For power analysis, D-box reduces the power requirements on average 16, 17, and 18% compared to pooling, interrupt, and insecure DMA methods of the HAL libraries. So the reason for this result is that because we use low-level drivers that access directly the peripherals, and we didn't use the drivers that are provided by the vendor of the development board. Finally, we apply D-box in a real-world scenario, securing a programmable logic controller. So the original application was totally monolithic, so that if an attacker takes control of the communication protocol Modbus, the whole PLC is compromised. To mitigate this risk, we apply D-box procedures to create two compartments supporting DMA. The first compartment contains a communication protocol, and the second one contains the control logic. The result of this test is that D-box improves security of the whole system, reducing the attack surface, and also it maintains the performance of the real-time operations, specifically the scan cycle of the PLC, which is quite important for these devices because the operations are time sensitive, and also it reduces the power consumption of the system. Conclusions. DMA operations are fundamental for embedded applications because of the performance, power, and especially security implications. D-box provides a systematic approach to enable secure DMA operations for compartmentalization solutions of embedded applications. D-box can improve the security of real-world applications, adding negligible overhead and reducing power consumptions. Thank you very much for your attention, and I will take any questions from the audience.
All right. Thank you.